enough to engage fully, but we can always take these conversations outside as well. So that 15 minutes caters for the presentation itself, as well as the engagements, comments, and questions. So we'll try our best to stick to 10, maximum 12 minutes for the presentation itself. And after that, we're going to have the comments, engagement, and questions. You'll be very lenient with me if I have to cut you short, because at the same time, we also have to keep track of time, if that's okay. Like I said, more engagement can always happen outside the venue. So at 10:30 just now, we will have our very first presenter. I think I can briefly already introduce him. Well, I have paper 51, and it's titled Emulating LTSP Clients with Minets and QEMU, enabling scalable testing for educational deployments. And our very first presenter, you are welcome to come on stage and start. Come.
Good morning, everyone. So my name is Wandi Demianju, and I'm from the CSIR, coming to present some of the wonderful work that we're trying to do for the public schools of South Africa. Since we all know that most of the public schools in South Africa, schools within the rural areas and township areas, they lack a whole lot of computing infrastructure, networking infrastructure, and storage infrastructure to help them conduct their mundane schooling activities, such as you. Okay, so now I'm trying to go to the next slide here. I'm not sure if this mouse is connecting.
Let's bear with us, he's on Linux. Please proceed.
So as I said, my name is Wandile, and the title of the paper that we're presenting today is Emulating LTSP Clients with Minets and QEMU to enable scalable testing and deployment for educational departments. So this is the outline starting from the introduction, the various initiatives in testing and evaluation for education, overview of emulation, which is like the whole solution we're trying to propose in testing of educational devices and supporting ICT infrastructure, the whole design architecture of the system that we're proposing, and the functionalities. We evaluated and discussed future work, and then we conclude. So as I was trying to explain in the start, is that computing infrastructure, storage infrastructure, network infrastructure is very essential in public schools as we store administrative records, academic records, and we conduct computer-based exams, access to the internet, and all the cloud computing hosted applications that help facilitate the learning process. So to conduct and deploy these computing infrastructure, storage infrastructure in these public schools, we typically provision them through computer labs. Computer labs can come in various deployment architectures, from thin clients, big clients, and zero clients. So thin clients are more of a low resource type of computer than your thick client kind of computer, which is like your standard computer that has all of the applications running locally, running on your CPU, your RAM, and you have a local, what you call a local operating system running here. So these are synonymously called fat clients because they don't rely on an external server for their computing requirements. But in a thin client, we rely heavily on an external server. As you can see here, this is like this external server. These are all thin clients, and they have low CPU, low RAM, and sometimes you can even have no disk on them, and they all just rely on this server. So it's a more cost-effective computer lab deployment as compared to having just fat clients connecting and to the internet or used as computing infrastructure. So this is more of a cost viable alternative for deploying computing network and storage infrastructure for public schools, particularly in developing countries. So here we have the Linux Terminal Server project, which is just I think client software that allows us to create what we see here. So there's a software that is running on this server, and this server allows it to serve its file system and computing resources such as your RAM and CPU, all these other computers. So the bulk of the computing is stored on this server, making it easier to maintain since you just maintain in one server. All these other computers are just endpoint terminals that the students can just use to access the computing storage house here. So there are a lot of planning that goes into deploying thin clients and computing infrastructure, which includes planning such as your client server ratio, your hardware specifications, your network speeds, and all those things related to security of the whole infrastructure. So to conduct those assessments, usually people go through paper-based assessments and physical deployments of studies. So we come in to offer a platform for emulated testing, digital platform to allow the testing of computing infrastructure, thin clients and thick clients using the LTSP server project, which is a free and open source thin client software operating on the Linux operating system. So it's a free system that public schools can just, with the procurement of hardware, of course, they can just download the software and install and have a ready, cost-effective computer lab to conduct their learning and educational administrative operations. So as you can see here in South Africa, we can see the Circular Living Lab, which is more like a piloting test bed that was conducted in Eastern Cape within 17 schools, testing the viability of using thin clients as computing infrastructure within public schools so they can access resources in the internet and conduct computer-based learning. So the project took around 10 years and a lot of money was spent on the project, and it ended up not being sustainable due to the funds, government funds that were lacking. Similar initiatives are also seen throughout Western worlds, Europe and America, interventions such as like educational test beds, which are more like co-creative platforms where everyone comes in and jointly collaborates with the teachers, the students, and the edtech suppliers to produce technology that is suitable for that particular school. So that reduces a whole lot of wasting money on things that would have not been successfully deployed or efficient for those types of environments. So we then come in with emulations to try and streamline the whole process of testing thin clients, testing them within emulated environment, a digital environment, instead of using paper-based methods or using physical deployment methods. We can rely on emulation. As you can see from this taxonomy here, we have simulators, emulators, and network test beds. And emulators lie somewhere in between. So you have your network test beds. Test beds are just like your physical hardware that you're using to test and run your experiments, as compared to simulators, which are just like your digital representation of the real thing, but lacking a whole lot of realism or aspects of the real world. So solutions that you develop in an emulator, you can't really take them and put them into production straight away. You still have to modify them and make sure that they are suitable for the environment that you're deploying them to. But in an emulator, solutions that you develop in an emulator, you can just take them straight away and put them in production, because emulators use virtualization concepts that are inbuilt within operating systems and kernels that have a high level of realism, a high level of fidelity, that the solution that you develop there will run on another Linux, will run on another computer, if you can translate to the different machine architectures that are supported. So we have 4 classes of emulators, which are container-based emulators, virtualization-based emulators, network-based emulators, and cloud-based emulators to just support the scalability and creation of more virtualized nodes, since virtualization consumes a whole lot of computing resources. Your CPU, your RAM, your disk is consumed a lot by virtualization technologies. So cloud environments are more suited for having these experiments. So you can model a whole school consisting of 500 to 1,000 computers, which is not really feasible in using one computer, which were some of the limitations of this study. So the container-based emulators are emulators that focus on using concepts just like namespaces, where you have Docker or LXC creating containers, which are more like lightweight versions of virtual machines. And then we have like virtual based emulation, which is just virtual machines creating the network. So using virtual machines to create the network, you have a whole lot of hardware level virtualization. So you can virtualize the CPU, your network interface card. You can also virtualize other things such as various kernels, and you can run multiple operating systems on one computer. And then you have like your network link emulators, which allow you to manipulate the connections between computers. In that way, you can measure the latency, bandwidth, or packet loss to try and investigate the quality of service of the applications that are running on the computers or from a different server. So they're very useful. So what we done here is that we designed this platform combining these three entities, like your container-based, your virtualization-based, and your networking features, to create this platform that allows us to create network nodes with hardware virtualization features and container virtualization features, and the ability to manipulate the links between the nodes that they connected. So we can measure things like quality of service, bandwidth, latency, throughput, and all those things related to the network specifications. So using this platform, you can model infrastructure, computing infrastructure, as if it was the real thing, exactly as how previously was tested physically in school. You can now then use this environment. So this environment consists of mainly Minets and QEMU, which are just your container-based emulator and your virtualization-based emulator. From there, you can just see the more granularized architecture, or the low-level architecture, which is this, which was consists of namespaces, of course, namespaces, and then we add QEMU. So the black parts of this architecture is more like the original Minet emulator, and then since it didn't support virtualization at the hardware level, we introduced another emulator called QEMU, which now allows us to create nodes with hardware virtualization features, nodes that can net boot, which is a very critical feature for thin clients. So thin clients require net booting because net booting helps them to access the server through the network. So this is how we can see the various thin clients from the emulation or the emulated platform to allow us to test and evaluate various thin client topologies. So this is an example of 5 LTSP clients with 5 users here. And then this is your typical Minet setup network. So it consists of a switch, 2 Minet hosts, and a remote controller, a router, and then one server. So controllers in Minet, maybe some people do know this, some people don't know this, but there's this new software. It's more like a network architecture that allows the network to be centrally managed and centrally programmed, so you can replace other traditional network elements like your routers that were previously hardware. You can make them software and run in decentralized controller called the SDN controller. So you can have for example, what we did here in this proposition that we proposed for South Africa, we created a computer lab, and this computer lab consists of two. So you can see here, these are two NCSP servers that serve clients, right? There are two, but instead of using a dedicated load balancer, we use the software load balancer, and it runs on an SDN controller. So the SDN controller, its job is just to manipulate the behavior of the network using a central point of the network. So now you don't have to configure each router or each switch throughout the network. You can just configure this central part of the network, and that central part of the network allows a high level of programmability to the network. So you can write SDN applications on top of that to automate network management. So that's really something that we need in South Africa in terms of IT support and network management, since we don't have really enough funds to manage all of those things. So we use the round robin algorithm within the REU load balancer. The REU is a SDN controller, so we use the load balancing application written in Python to be able to provision the client's connections to these servers. So this is a more cost-effective way of having this infrastructure and also allow scale. So you can also see the traffic exchange within this, so that it's real traffic. You can see the protocols here, you can see the packet numbers and IP addresses and MAC addresses, reflecting to you that the level of realism of this is very high. You can conduct these assessments here and then put these solutions directly to a real world. So these are like the performance
challenges, and one of them is climate change and its impact on the environment. So conventional designs mostly rely on those three aspects of base stations power supplies. They often use grid power supply. Then with the advent of load shedding and all of that came backup generators because the network uptime has to be maintained despite all the challenges. And that coupled as well with UPS systems, of course, subjected to the fact that they short-term backup. And all of that drives high operational costs. It's also identified that there is energy wastage in traditional base stations, and that's because we have a static energy consumption whether we've got high traffic load or not. And that leads to inefficiency. These inefficiencies are exacerbated by dynamic network demands because we do not obviously have constant network demand. Emerging imperative for sustainable power supply designs is driven by many aspects. SDGs on one hand, the whole idea in 6G and beyond to move towards self-sustainable networks, not just self-organizing networks where we are at. The aim of this research was to assess energy efficiency strategies in base station designs. We want to explore integration of renewable energy sources on the base station power supply design, address challenges in dynamic energy management, provide sustainable telecommunication solutions for 5G networks and beyond. That's the ultimate goal of us. The research questions that we posed while embarking on this work are elaborated there. There's one related to energy efficiency, the other one which with the objective to drive cost low. The other one is related to CO2 emissions with the objective to drive environmental impact to be low. And the last aspect is actually a bit in contradiction with these two, but it's to say when we drive this agenda, are we still maintaining high network uptime? So are we still maintaining communication? Because at the end of the day, communication must still happen and reliably so. So that table summarizes more or less the current state of the art as far as base station power supply design is concerned. But we noticed as a summary that traditional designs rely on grid power and diesel generators mostly. Renewable integration, we picked up that in already proposed work. Sources such as solar, wind, and of course coupled with energy storage systems. But the challenges include network intermittency as well as variability of the network demand, like I mentioned. Therefore, dynamic power management systems are where the trend is going. And this work aligns very well with that. So some of the current design approaches that integrate already renewable sources, such as solar and wind, present the benefit of reduced reliance on non-renewable, which drives low carbon emissions, of course, and also reduces operational costs. The challenge, however, is the intermittency, like I mentioned, and variability of network renewable sources. So most of these approaches basically respond to this equation where the solar power plus the wind power is maintained or trying to be balanced against load, power, and storage. So what we have in storage and what the load requirements are. And that's what we want to maintain the whole time. There are some advanced modeling techniques that are proposed as well, such as stochastic optimization, which accounts for renewable energy variability. So this is one of the works finding literature that is trying to address the intermittency. Predictive control algorithms also for power management and intermittency. Dynamic power management, some work, load-aware resource allocation. They propose that to improve energy efficiency. We also have some work that have strived to have a robust real-time algorithms to ensure network performance. So that's now on the network uptime. This work identified some research gaps, and these are presented on the left. And therefore, associated with these research gaps, we propose some contributions. And it proposes a novel methodologies for power supply design. We integrate insights from electrical engineering, renewable energy, and telecommunications, so it's really multidisciplinary and very suitable for this conference. and it lays a foundation for efficient and sustainable base station power systems. Like I said, that's where we want to go in terms of self-sustainable networks. In terms of the design approach, we combine solar, wind, and conventional power sources. Advanced energy storage for managing variability is proposed, and predictive control algorithms for dynamic power management. That's just half of the flow diagram is for how the logic is set up. The modeling behind takes into account, so we go, if you remember the original equation, now here we bring in renewable as a whole, and we try to keep that, in this case, equal to solar and wind, because that's all we have. But we have to balance reliability as we use renewable energy in our model. And that's the main challenge, because the intermittency can be quite well managed between solar and wind, and even on a very dire situation, rely back to traditional power sources. So the storage is a big part of this work's contribution. So, and it's mainly aimed at mitigating intermittency of renewable sources. And the dynamics behind it, which are more formulated in terms of prediction. The next energy storage aspects or point or iteration is computed in terms of the current one, added with the charge efficiency that we currently have, multiplied by the current power requirement of the load, basically. So a lot more details, of course, are provided in the paper as for the whole mathematical workout, which will take a bit long to dive in, but the idea really is to coexist solar, wind, to drive the energy availability, but at the same time, make sure that we have, in worst case scenarios, the ability to backfall on the power source itself, and that all of that happening dynamically. And at the same time, that then requires us, in terms of storage, to dynamically study the behavior of the storage system and predict the next move, so that we can know to which energy source to fall back to. Well, some robust control algorithms for dynamic power management, which is the other contribution aspect of this work. This goes through adaptive power control, and this is formulated as an optimization problem whereby the algorithm seeks to minimize total operational costs. And total operational costs is obviously dependent on the power balance equation, and it also factors in it the predictive maintenance and fault detection is a very, very important aspect. So at the end of the day, the entire hybrid system purpose goes back to minimizing total costs. Well, the performance evaluation, we use 3 key metrics: energy efficiency, reliability and cost saving, reduction in carbon O2 emissions. This work was implemented for now on simulation using MATLAB Simulink, and we used about 2,000 devices, and the metrics were then computed through the algorithm to more or less simulate the behavior over a week of operation. In terms of energy efficiency, it is found that the hybrid system that we propose is actually doing relatively better on almost the whole week compared to the traditional approach. And that's basically is, especially in terms of energy efficiency, is the fact that the constant energy consumption that we observe in traditional networks is therefore mitigated, and by the use of dynamic power supply against the actual estimated demand, instead of a constant power supply. Now, the CO2 emission aspect of it, of course, in the paper we have a lot more modeling on how we come up to computing this, but also once more the proposed approach performed much better throughout the week. And we take a week because the literature informs that because we are doing renewable, most of the renewable energy sources have got a weekly pattern in terms of their behavior. We also assess the network reliability, And this obviously was measured using point-to-point, device-to-base station communication, both in the upweek and downweek, and computing throughout the week, the network packets that we drop, and repeated transmissions, and all the network the network transmission and reception challenges, and based on that, we then computed an overall percentage of network reliability. And once more, the proposed approach is very promising in terms of performance compared to the traditional approach.
3 minutes left.
Thank you. Lastly was cost, and this is more estimated based on the current, a typical base station setup and the cost of equipment that is there. And once more, despite one would have thought the inclusion of renewable energy would drive the cost very high, but despite that, the cost efficiency, meaning when we go beyond what we spend and we look at how much energy we consume, which is also cost saving, as well as the operational benefits and all of that, in a more financial model, we came to the conclusion that the hybrid system has the potential to perform better than conventional base station power supply designs. In short, really, is that there is room for hybrid design as we integrate. I would even say it's a must that we must bring in renewable energy in base station power supply designs because we want to meet the self-sustainability goal of next generation cellular networks, and it's prone to yield a lot of benefits. However, there's a lot of challenges related to balancing energy efficiency, carbon emission, and network reliability or uptime. And that's the real question. As you can see, it's really more of a multi-objective optimization problem, which this work attempted to solve. But this work so far has been at the conceptual level and has been done fully in simulation. As the next step, we want to look at other renewable integration, but the second point is more where we will go next, where we look at scalability and deployment, looking at larger networks, more than 2,000, which are more and more realistic, and also, very importantly, trying to harvest data from the real networks now. I thank you. Yes, please.
Thank you for the presentation. From number one, you're working on the base station, 5G base station.
5G and beyond.
So I want to ask first, what's the component system you're using? Storage. What type of storage system are you using?
Okay, storage is battery primarily, which naturally drives cost. But to compensate for that, we have UPS systems and supercapacitors in most systems.
So that one brings me to the next question. Like if you are working on the 5G base station and you're using battery, how did you leverage the peak power ratio of, because 5G always has a very high average power ratio. So how do you leverage the battery and the peak power ratio of the 5G?
I'm not sure I follow the question, but okay. Leverage, you say. Okay. Are you talking in terms of energy harvesting in that context? Yes. Okay. So yes, that's another very promising area of research to look into. However, the main issue of RF power harvesting has been the inefficiencies of the power supplies design itself. You almost do not necessarily get the benefits of the RF power harvesting. Sometimes the efficiency is so low that you drive more power in trying to harvest very little. So, but yes, there is room for tapping into it. I agree. Thank you for your questions. Yes, please.
Do you mind going back to the that signal, the network reliability signal?
You mean the result?
Yeah, the signal.
That one?
Did you take consideration of the varying factors on the PD and the wind, like the temperature and duration of the wind, in terms of generation.
Yeah, so yeah. Yes. Using a purely optimization, whether it's a traditional or modern technical optimization, is definitely identified not to be enough for this kind of work. So in the future work, I think I mentioned it, there's a need to definitely bring in machine learning and other techniques, right, to have the whole solar profile and irradiation profiles for better and more accurate predictions. Definitely. That's not considered as yet, but that will definitely contribute towards further studies. We just wanted to go back to traditional methods and modern techniques of optimization to just try and see the potential that this proposes. But yes, definitely there is room for using machine learning and other techniques for such. Okay. Thank you very much. Our next presenter paper 93 in the room. Yes, 93.
Or do we go in order? I'm 92.
Yes, I was going to go. Let me see. Right. So 93 was supposed to be next, you then? 93. Machine translations. That's 93. Yes, please. Okay. Yes, our next presenter already sets up. His work is on machine translation for morphologically rich, low resource